Okay, we are going to go over a few more questions about gravitational fields. So this is like part two. So in the first question here, we're going to try to figure out how much energy is required to launch a weather monitor 120 kilometers into the air. Okay, just make sure my pen's working here. Okay. So we are going to first, I'm going to convert this to meters because this should be in meters. So I'm going to convert that to 1.2 times 10 to the 5 meters. Okay. So if you're in grade 11, you would have answered, you would have done a question like this by using an equation that would have looked something like this, where the work done was the function of the mass, 700 kilograms, times g, times the change in height, which is 1.2 times 10 to the 5 meters. And that would have given you an answer of about 8.2 times 10 to the 8 joules, okay? But because it's such a large distance, we should realize that g is actually going to change. So this equation that we would have used back in grade 11 might not be as accurate when it comes to distances probably, I'd imagine, greater than at least 100 kilometers. And in this case, we're looking at 120 kilometers. So there's going to be a discrepancy between doing it this way and doing it the way we looked at in the previous session, which is the work is defined as the difference in energy when we have it set up as this equation. Okay, and this equation is going to give you a slightly different answer. I mean, be close, but this will be more accurate. So we put in our values times the mass of the satellite times the mass of Earth, because we are leaving Earth, okay, over R2. R2 is the radius of the Earth. So the radius of the Earth is about 6.3 times 10 to the 6 meters, plus the height of the satellite. So if we add those two together, it'll be about 6.42 times 10 to the 6 meters. Minus a minus, so it's plus 6.67 times 10 to the minus 11. Again, times the mass of the satellite times the mass of Earth over R1. R1 in this case would just be the radius of the Earth because the satellite keeps calling it a satellite, a weather monitor, which, because we can call it a satellite, I don't know, would have started at the surface of the Earth, which is 6.3 times 10 to the 6 meters. Okay, so if you add these two up, you get an answer of 8.7 times 10 to the 8 joules. And you can see that there's a discrepancy between these two answers. Okay, so for distances, I would imagine at least 100 kilometers or more, it's better to use this equation. For distances like maybe 10 kilometers or less, I would imagine using this equation would be very, very similar. But anyways, okay, let's move on to the next question. All right, number 2. Okay, what happened? Screen disappeared. All right, hold on. Let me just pause the. Okay, we're back. All right, technical difficulty. All right, next question we have, it's an escape velocity question. So what we're going to do is we have a satellite that's orbiting around Earth at an altitude of 3,700 kilometers. So what that means is that from or relative to the center of the Earth, its distance would be 6.3 times 10 to the 6 meters. That's the radius of the Earth, plus this distance, which would be 3.7 times 10 to the 6 meters. So its actual distance to the center of the Earth is 10 times 10 to the 6, or 1 times 10 to the 7 meters. Okay, so what we're going to do is we're going to first figure out what is its actual speed. If you remember previously, we were able to figure that out by setting the centrifugal force equal to the universal law of gravitation. That would give you the mass of the satellite times v squared over r is equal to big G, mass of Earth, mass of satellite over r squared. So therefore, if we rearrange, you can see mass of satellite will cancel out, and then r would be moved over to the side. So it would be just v squared would equal g m Earth over r. So we can say then that v is g m Earth over r. Square root of that. Okay, so then we can figure out what the speed of Earth, speed of the satellite is. 6.67 times 10 to the minus 11 times the mass of Earth. Okay, over the radius, this distance to the center, which is 1 times 10 to the 7. Now, that would give us a speed of approximately 6.3 times 10 to the 3 meters per second. Okay. Now, what we're then going to do is we're going to figure out what is the escape velocity. So if you recall from the previous lesson, escape velocity is the minimum kinetic energy required to get an object off a planet or some other object, like the moon or a star. It's enough energy, kinetic energy, to get to a point in space where if we add these two values, they equal 0. Because as the object is leaving, gravitational pull is slowing it down. So it's going to slow down over time. But as it gets farther from the object, whether it's a star or a moon or a planet, gravitational force is weaker. So the gravitational energy is weaker. So the minimum speed would be to get to a point where in space where there's no more kinetic energy because it's slowed down to 0, but there's also no more gravitational potential energy because that's also reached 0. So then we could say EK is equal to negative EG. And if you remember from the previous lesson, EG is negative GM1 M2 over R. So we can then say 1/2 mv squared is equal to, well, negative of a negative would give you positive G M1 M2 over R. This is going to cancel out because obviously one of these is the mass of the planet, the other one's the mass of the satellite. So we'll just say they cancel out this with that one. So we're left with 1/2 v squared is equal to big G M1, which is the mass of the Earth, over R. So then we rearrange v squared is equal to big G mass Earth over R times 2. Okay, and then we can just take the square root of all of that. So if we do that, then v would be the escape velocity would be big G, 6.67 times 10 to the minus 11 times the mass of Earth. All right, over the radius being 1 times 10 to the 7, all times 2. Okay. And then we take the square root of that. If we do that, we get an answer of about 8.7 times 10 to the 3 meters per second. Okay. So this over here was the speed of the satellite going around the Earth at this orbit. This is the escape velocity. So obviously the difference between the two, the difference between these two values, which ends up being about 2.4 times 10 to the 3 meters per second. That would be the amount that the object would have to increase its speed by. So if this object increased its speed by 2.4 times 10 to the 3, it would be able to leave Earth's gravitational field. Okay, that's number 2. Let's move on to number 3 now. Okay. So number 3, we have an object leaving Mars and exiting the solar system. So it's actually kind of related to what we were just doing before, where this means it's going to get to a point where the kinetic energy and the gravitational potential energy will be 0 But in this case, it's got to leave two things. It's got to leave not only the planet, Mars, but it's also got to leave the sun. So that's going to add up to 0. So what we could say then is that the kinetic energy, which is 1/2 mv squared, say mr for the rocket, is going to equal negative Eg Mars plus negative Eg Sun. Okay, so if we fill in some values, we know that this is a negative of a negative, for like as in the previous example, because remember, Eg is negative initially, so now this becomes positive. So 6.67 times 10 to the minus 11 times the mass of the rocket times the mass of Mars. So the mass of Mars is 6.4 times 10 to the 23. Okay. And that's over the radius of Mars, which is about 3.4 times 10 to the 6 meters. Okay. Plus 6.67 times 10 to the minus 11 times the mass of the rocket times the mass of the sun, which is about 2 times 10 to the 30 over r. Now r would be the distance from the sun to Mars, which is about 2.2 times 10 to the 11 meters. Okay, or 220 billion, sorry, 220 million kilometers, not billion. Okay, you can see that the mass of the rocket is going to cancel out. And then we can multiply everything by 2, get rid of the half, multiply all this by 2, and then we can take the square root. So now V is going to equal the square root of the sum of these two values, G, mass of Mars over the radius of Mars, plus G, mass of the sun over the distance to the rocket. The sum of that times 2, take the square root of that, we'll get an answer of approximately 35,174 meters per second, or we could just round it off to about 35 kilometers per second. Okay. All right. Last question. Okay. Is an object actually matter leaving coronal mass ejection is when a star spits off matter into space. Plasma is just super hot material. So this super hot material is being shot off the sun, off the surface of the sun. Okay, and we're going to try to figure out what is the speed of the plasma when it is about 150 million kilometers from the surface of the sun. Okay, so what we're going to do is we can say something like this. We could say that from what we learned last year, the left side energy always equals the right side. So we could say the kinetic energy at A plus the gravitational energy at A, and that will be at the surface of the sun, is going to equal the kinetic energy at B plus the gravitational energy at B. Okay, we are trying to find, let's say we'll call position B when it's 150 million kilometers from the sun. So what I can do is I can move EGB to the other side. Sorry. To solve for the kinetic energy at point B. Now, if we put in some values, the kinetic energy is 1/2. Now, at A, it's 3,000 kilometers per second. So 3,000 kilometers per second would be 3 times 10 to the 6 meters per second, plus the gravitational energy at A. again, gravitational energy is negative G times the mass of the plasma times the mass of the sun, okay, over R, which is, it's at the surface of the sun. So the surface of the sun has a radius of about 6.96 times 10 to the 8 meters, okay? Okay, so now that is going to be minus a minus, so plus G 6.67 times 10 to the minus 11 times the mass of the plasma times the mass of the sun over RB. Now RB is when it's 150 million kilometers from the sun. So 150 million kilometers would be 1.5 times 10 to the, wait, hold on, 10 to the 11. Is that right? 1.5 times 10 to the 8. Yep, 1.5 times 10 to the 11 meters. Okay. So first thing you can notice is we can get rid of the m. Oh yeah, and that's got to equal, sorry, 1/2 mv squared. Okay. So we can get rid of the m. Second thing we can do is we can get rid of this half. We're going to multiply everything by 2. And then we could take the square root of all that. And that would give us the velocity at this point, which would be a velocity of about 2.9 times 10 to the 6 meters per second. I think it's actually about 2.94. So you can see that it's only really decreased about 0.06 times 10 to the 6 meters per second. Let's slow down a little bit. One interesting little point, when you compare these two values, if you do the calculation, you compare them, this value ends up being about negative 1.9 times 10 to the 11. And this value ends up being 8.9 times 10 to the 8. So just so you understand, this is the gravitational potential energy relative to the sun, and the object is on Mars, okay? And this is the gravitational potential energy relative to Mars, and it's on Mars. And you'll notice the the gravitational potential energy is a negative value, right? In this case, it ended up being positive, but when we compare these two values, you'll notice something. The binding energy on Mars is way smaller than the binding energy relative to the sun, even though it is 150 million kilometers from the sun, which just tells you just how massive the sun's is and how extensive its gravitational field is. Anyways, and that's it for those 4 questions. Thank you.